Hi folks, this is the third video segment that I'm doing to discuss the FEA native solver in Catia for composites. Okay, now the first one was general comments. The second one was actually uh, the problem that you're seeing here on the screen, except that I used one ply of a total thickness of zero point 0.1. Okay, I'm going to repeat that problem, except that I will be using two plies both at the same orientation 30 degrees, and each one of them having a thickness of 0.05. So when you look at two of them, the laminate is going to have the same thickness, double of 0.05 is zero point 0.1, and the results are going to be identical to the first problem that I did. It's a good idea because you get to see some repetitions, first of all. And the second thing is that I made a mistake in the first video segment that I later corrected, and I indicated in the description of the YouTube description. This everything went well except for the fact that Tsai Wu and the Hoffman criteria were not matching the analytical calculation that I had on the slide. The reason was that this shear strength, instead of putting it in the box which actually specifies it, I put it in the wrong box, and therefore shear strength was assumed to be zero, and therefore my numbers were different from Saibu and Hoffman's uh, number from hand, numbers from hand calculation. So anyway, that, that that's taken care of. Now, a couple of things. I got the idea about these simple, straightforward problems from this site, which is from this particular YouTube site, and it's something that's done by Dr. Howard. And so these numbers that you see here are coming from that particular site. Okay. Now, if the first time that I did it with one ply, that laminate was neither symmetric nor balanced. Okay. When you do it like that, then the laminate is symmetric, but still unbalanced. The fact that it's unbalanced, it means that when you load it in the axial direction, you not only get stretching, you will also get a shear deformation. That was clearly displayed in the second video segment. Okay, now the fact that it's symmetric means that there is the matrix B in the terminology of composites is zero, and that means that in plane deformation and bending, or out of plane deformation are decoupled from. There is no out of plane deformation here because we didn't apply any moment, and the matrix is symmetric. Okay, so we're going to do this problem. Remember, these are roughly the properties of carbon epoxy lamina, and we're going to input these, and we're going to input those, and work it out. Now, uh, let me first tell you, this the stuff here is is not in uh, is not in the CATIA's composite database. Okay, so I had to go and create my own. Let me see now. I had to go and create uh, my own catalog of the composites that I want to make. And the first one that I made was for that uh, one ply. Now I can use that. I can use that. The only thing is that the thickness, the cute thickness, which was zero point 0.1, is going to be 0.05, because I'm going to be, I need really two of these to put together to get a total thickness of zero point 0.1. Now, however, I'm not going to do it. I'm going to do it from scratch, and I will pretend that actually uh, this was a we didn't have the properties from the first problem. So let me open this, and this is the one that I created. So I'm going to create another one. This is, see, it says new material here. And I'm going to change the name of this thing, properties. So this is going to be 2 plies plus 30 uh, underscore plus 30. It's crazy because everything that I input in here is going to be the same one that I had in the previous one. The only difference is the cured thickness that's different. So it's crazy to do it like this. It's better to change the cured thickness here and then use that. But this is okay because it'll give you another practice. So apply. All right. Notice that the name changed here. Now this is a composite and the cure thickness is going to be 0.05. In the previous one, I put 0.1, 0.05, okay? And it's unidirectional. And then analysis, a 2D orthotropic, and everything here is going to be the same as what I had before. Hopefully I won't make that mistake that I did before. So it's going to be 2e to the 6. This is 1.2 e to the 6. This was 0.25. Shear modulus in the plane 0.8 e to the 6. And for the other two planes, we use 0.4 e to the 6. These last two are not specified in the table that I gave you, and it's not used, but I will use these numbers, e to the 6. I'm sure you can run the problem without putting these things. Yep. Now, the mistake that I made, well, let's put these things. These are longitudinal tensile strength. This was 300,000. Compressive, 150,000. And I made a big fuss of the fact that in the ordinary literature, they use a negative sign here. Most documents in the literature minus sign. And I didn't pay attention to that, so I put a minus sign here, and Catia would not run, and it took me a while to find out what the issue was. This number, although it's a compressive stress, okay, or strength if you want, should not be used, should not be written as minus, okay. Tensile in the transverse direction is 7,000, and uh, in the for the compressive, it's going to be 25,000. Not negative 25,000. Now the mistake that I made for shear, I accidentally went here and put down 14,000. I was not really looking at the title of these. You have to scroll down and down here, shear stress limit in the XY plane. That means shear strength 1400. Okay, and say we okay, and then we save. Okay, now I can use this. The stuff here is exactly like that, except for cured thickness. Okay. So I'm going to close this, and we can start our Catia file part. I'm going to call this thing, I don't know, 2 plies. 2 plies. These are just bookkeeping things. Uh, you don't have to do it if you don't want to. Okay, good. So let me move these things up there. Okay. Now, we are in the composite design. I don't want to be there. I want to go and create my model. So I have to go to shape, generative shape design. But this is a very simple geometry. You can also do it in mechanical design, wireframe design, service design. But I will do it in the richer version of the workbench. So generative shape design. All the steps are going to be repetition up to a point, and then because there's 2 plies, we'll see that I have to do something else. Okay, so sketch on that XY plane a rectangle which is 4 inch by 1 inch. Just to mention it. is 4 inches, and this is 1 inch. Exit, and you fill this thing. There it is, fill, right? You fill this closed curve to the surface, and you join it. And I told you why we wanted to join this thing, because when you join the surface, it puts a direction associated with it. Okay, so direction associated with it. Oh, not sketch. I'm sorry. Join. Sorry. I turn this thing around. Oh, something is not. Oh, the fill. Cancel. I accidentally. Let me delete this. Let me delete this. Or actually, you know what? I didn't want the sketch here. I wanted the fill. That's what I wanted. Okay. Okay. Let me show you. When you double click on that, when you double click on the join, which is joining the fill, you get an arrow. This arrow indicates the positive side of this surface, and the other side is the negative side. The reason that I bring this up is that when the surface is meshed with shell elements are lie in the surface, okay, lie on the surface, and they have local coordinate system. Directions 1 and 2 are in the surface, and direction 3 is perpendicular to 1 and 2. Now, uh, the direction 3 of the shell element is opposite of that. So if you insist on the direction 3 of the shell element to be up, for visual purposes perhaps, you flip this thing down so that the shells are going to be so that the third direction is up. You say, okay. Now, one thing I forgot to do last time, which I'm not going to do it again, is I'm going to create a coordinate system here. One is aligned with that. So where is the coordinate system stuff? Here is tools. There is the coordinate system. You can see the axis system. When you create an axis system, you can create as many as you want. The first one is going to be, the default is going to be aligned with the global XYZ, which is right here. You can see it, XYZ, parallel with these. Now, first of all, it's going to be placed at the global origin of the part, which is 0, 0, 0. Now, I don't want this thing to be there. I want to deliver it to be the left. So I'm going to say create a point, and my y, I'm going to make it negative 1. So it's going to put the coordinate system right there. We say OK. Now, you see it says current. The current is checked. And what that means is that whatever coordinates I put in my Catia dialog boxes is going to be with respect to the current coordinate system. Now, if I don't want this thing to be current, I still want to measure my 0 from there, which is fine. There's nothing wrong with it. You just uncheck that. Notice that the solid becomes dotted. Or you can leave it like this, and then you can select this, right click, go all the way down, and it says set as not current. It's not the same thing. Now, I called this thing, I renamed this thing and called it aligned with global X, Y, Z, right? Global X, Y, Z. And in parentheses, I'll make this thing my indicate that this is going to be used also as my rosette. Now, if you insist on making another coordinate system just like that for your rosette, feel free to make another one. But I put them together, and there we are. You can see that. Okay. Now I'll do another one which is aligned with that, except that rotated by 30 degrees about the z-axis. So let's do another one. Coordinate system. Create a point. So it's going to be -1 from this point, and then I go that way, so xi increases by 1 right there. So this other coordinate system is going to be placed at that location. Okay, and I want this thing to be rotated about the z direction, positive z direction, by you put the cursor in the z, right click, rotate 30 degrees. See, it's rotated by 30 degrees because now X is going to be aligned with the fiber of these laminas. Okay, and I indicated why is it that I want this to create this coordinate system. where X is aligned with the fiber direction, because when you plot the stresses and things like that, for hand calculation purposes, we're going to compare it with the fiber direction, transverse direction, and etc. Now, I don't want this thing to be current. Remember, you select it, right-click, set not as current, and let me rename this thing, properties. I'll call it rotated Z, global Z by rotated about Z by 30 degrees, plus 30 degrees. Okay, good. All right, we are done here. So now we're going to go and create our laminate, okay, or plies. So to do that, you have to go start. You go to mechanical design, down here to composite design. Very good. Now remember, I could have created my coordinate system here. Look, there is an axis system right up there. You can see that. Okay. All right. So the first thing that we need to do is to create the parameters. Right here, composite parameters. You click on it, and there are no materials yet. So we go add a material. Go and find that the catalog that I created on my desktop is this one that I created. Say OK. Select it. Notice that there's two materials there. You can see that. One of them was 1 ply, the other one was 2 ply. Now, obviously, I want 2 ply. 2 ply. See, I want the material right here, 2 plies. Okay. And notice that it picks the right one. The cured thickness, the cured thickness is 0.05. The other one, cured thickness is 0.1. Okay. Now I also mentioned that if you want, you can put the other material here. If you want, you can put another material, for example, from the Catia database here. But you're not going to be using it. Just to, just to remind you again how we do that. Add a material. Go to the composite material. This is Catia's composite material. I don't know. I'll put glass. Say OK. Here, right here. But I'm not going to use it. Okay, so I don't know why we want to do that. But okay, that's fine. Now we go and create our select our rosette. Add a rosette. You go and either pick it from the screen or from the tree. Either from the screen or from the tree. You can see that. This is the rosette that they put in the Catia program after, I don't know, 2000, maybe 2009, 2010. It's kind of, I don't like it. I'm going to hide it. I suggest you look at it if you haven't seen it before. Okay. And so we created our rosette right here, and then the direction. Now the direction, I want a 30-degree direction, and I'm going to create one right here. Add the direction. I'll call it my direction. Okay. I don't know why I call it my direction, and 30 degrees. And for color, I'll use a different color, so maybe brownish. Oh, okay. So I think we have done everything that we needed here. We say okay. So notice that the material properties were set. In fact, if you look at the material, there is this one that I'm going to be using. This is not. I'm not going to be using this. It's from Catia database. Orientation. There's a whole whack of them. All I want is my own direction, which was 30 degrees right there, and rosette is of course down there. You can see that the rosette is right here. Okay, there. Okay. Now in the second tutorial with a single ply, I did this thing with the ply method, okay? Manual ply method, manual ply. When the problem becomes complicated, for example, there are several areas that are, laminates or laminates are stacked on top of each other, etc. It may be better to do a different method called the zone method, but this is simple enough. We're going to do manual ply. So I'm going to the first thing I need to do is to create a ply group. Okay, to ask a bunch of questions. First of all, what is the surface? There's a surface. What is the rosette? The rosette is rosette 1. And if you say lock plies draping direction, it stacks them in this direction, in the direction like that if you lock it. Okay. Now I want to lock them so that they build up in the Z direction. So I'm going to flip this. This is the draping direction of the plies group, and then I say, yeah, lock it. So next time you make a ply, then use this as the direction of the ply. You say, okay, good. So notice that a ply group has been created here. Now I'm going to create a ply. This is a ply. So this is all happening in the plies toolbar. You can see that. This is a ply. You select it. Bottom left corner, it says select a ply group or a sequence, etc. So here is the ply group. Okay, it says, what is the boundary of your ply? Well, it's the sketch. I can use the sketch right here. I can use the sketch, or I can select it from here. It doesn't matter. Same thing. Notice that this is going to be the boundary of my first ply. And uh, I'm going to be using two plies. Okay, this is the material, and the direction is my direction, which was 30 degrees. Okay. Now, one other thing I want to tell you is that over here, notice that the contour does not have to be a close contour. It can be a bunch of curves, but collectively, when you select them, add them here, they must create a closed curve, closed contour. Okay, so we say, all right, here is my ply number 1. Okay, now another one, you select this ply again. It says, where do you want to put it? Well, I can put it in this ply group. I can put it in that sequence. You know, these are good things, important things, but this is not part of the FEA simulation, okay? If you're going to work in this business as a designer, you have to know the composite design toolbar very well. But I'm not doing these segments for that end of it. But I'm doing it for the FEA analysis. So anyway, so here's my ply group. Again, for the boundary, for the contour, I select that same sketch right there. For attributes, this is the material that I want to use, okay? And again, direction is 30, my own direction 30. Good. So here is your second ply. You can see that. All right, let me close these things. We are done here. First thing we should do is to go and save all this stuff. File, save management. There is the part, save as, a folder. I created something, folder like that, and this is the name, fine, and we say, okay. All right. Now we're going to go to analysis and simulation, advanced meshing tool. Now remember, you can skip this step, advanced meshing tool, and go to generative structure analysis and use shell elements, which are the standard shell elements and the only shell elements that you have in generative structure analysis, namely these 3-noded or 6-noded triangular shapes. But I want to use a nice quad element, 4-sided element, so I can use surface measure or advanced surface measure. We use surface measure. Okay. So select the surface. This red arrow means that the normal to the shell element, direction 3 to the shell element, 1 and 2 is in the plane of the surface, and direction 3, which is cross product of 1 and 2, is going to be pointing in the direction of this red arrow, which, remember, I flipped the arrow for join to make sure that this guy will point up. This is always the opposite of the direction of the arrow in join. Okay, we want a parabolic, we want a quad only, and then that's it. You say okay, nothing fancy, and then you mesh it. There's how you mesh it. Mesh the part, mesh the part, mesh the part, and say okay, and exit. Now, the mesh is made here, so, but I'm not going to display it there. We can go and work it out. First thing I do, I make sure that the analysis, cancel, the analysis is part, because where is that? File, save management, analysis is right here, save as, in that same folder, desktop, same folder. I can call it anything I want. Since there's going to be only one analysis, I'll call it analysis 1. Okay, we now switch to generative structure analysis. And if you want to see your mesh right here, mesh visualization, change the rendering so that you can see the edges right there. Okay, now let me deactivate this. If you want to see the local coordinate system for the shell elements, so you put the cursor on nodes and elements, right click, generate image, and says local axis symbol, say okay. And if you zoom in, you see that what it is that this is the local coordinate system for the center of every element. 1 and 2 is in the surface, in the surface, on the surface, and 3 is perpendicular to surface and is by the cross product of 1 and 2. The right hand rule normally is in the upward direction. I just wanted to show you what that thing is. So let me just keep that in mind. By the way, look, keep this figure in mind, 1 2 3, but when you go to the other side, 1 2 3, 3 is up, but 1 and 2, the directions change. As a matter of fact, if you're using triangular element, the 1 and 2 is kind of very weird. It's not nice and you parallel like that. Just remember this thing when we display the stresses later on. Okay, deactivate this. All right. So first of all, I have the sketch. This is the sketch. You can see it's showing. I can hide it. And there's more stuff showing here because these are the plies. I can hide them one by one, or I can go here and say hide the entire stack. Hide. Now, this is the sketch. Notice that only the edges, the black edges show. This is where you can apply loads and restraints and things like that. Okay. So first thing is I'm going to apply a edge. Where am I? Did I mesh it? Yes, I did. And I just noticed something accidentally. I think I erased some. Oh, I know what happened. When this dialog box showed up here, remember when I went to Advanced Meshing Tool, I got a dialog box here. Which says static. I forgot to say okay, so I just, by doing the next thing, I just close that accident. This is why you don't get to see any loads and restraints and things like that. Yeah, but that's very easy to do. So you go to insert, static case. Okay. We don't have anything here. We say okay. Notice that this is where the loads and strain and loads and uh, restraints are going to go. I didn't get this in the present tutorial because I was too uh, too much in a rush. When I got a message here that this is static analysis or dynamic, etc., I should have selected static and say, which is the default, and say okay. I forgot to do that. This window, this dialog box closed. This is why I never got this. So the cure was I manually inserted insert static case, okay, and then I chose the default because nothing was done on it. Okay, so here is now you can see that all these things are lighting up. Okay, so let's go and apply our load. So the load, we know that it's 1,000 pound per inch. What I'm going to do is this is force density, which is force per inch. So you click on it, and again, I'm going to pretend that you didn't see these numbers. Okay. So the first time that you do it, you get this. So you select the edge, and you have to put down here in the direction X 1,000 pound per inch. So I say 1,000 LBF underscore IN. I could not see where in the CATIA you can actually set the units of density, line force density. So it seems that it's always Newton per meter, and then you have to put the correct units there, and it's going to convert. That's where that 17,000 showed up. That I say pretend you didn't see it. I changed that to 0, and we say okay. And if you zoom in, you see that there is an arrow here. There's 2 arrows here. So on this edge, that kind of a force density is applied. Now on the other side, it's exactly the same thing, except that the number is negative because it goes in the other direction. You put a negative here, okay. To zoom in, see that the force in the other direction. Now, as far as the restraint goes, uh, if first thing before we apply the restraint, let me go ahead and apply my properties, the properties up here. Okay, so if you're dealing with shell element, and you are under normal circumstances, if it's not composite, then all you have to do is to specify the thickness of the shell, which is this. But if it's a composite, then you have to say impose composite property. You click on it, it's going to ask you a question. It says, what is the support? In other words, where are these things going to be stacked on top of each other? It's right here, this face. And we're going to do it by ply. And now you have to go and say which ply. So I'm going to select, I go to the rest of my tree. I expanded this so that you can see it. You go to stacking sequence. You can either select ply 1 and ply 2, or you can select the entire ply group right there. So these two plies are going to be selected automatically. Now this symmetry, I discussed it in the video segment 2, the previous one. It's very important. So what that means is that these two plies are so that one of them is above this reference surface, the other one is below this reference surface. So it's symmetrically placed about this reference surface. Okay? If you don't do that, when you apply a load like this, it's also going to bend. Okay, so we say, all right. Now, if I run this thing, it's going to bomb out because this structure is free to move as a rigid body. So there are different ways of fixing it. The way I did it, I used the so-called 1, 2, 3 rule. You can do other things. There is also a this dangerous thing to use if you don't know what you're doing. This will apply the 1, 2, 3 rule. As a matter of fact, you know what I'm going to do? I'm going to run it once, and at the end, I'm going to come back and run it with this to show you that uh, it'll work. It'll probably work, but sometimes it doesn't. This is why I'm not very keen about it. Now, if you want to know what this thing is, what the 1, 2, 3 rule is, I suggest you go to the channel. There's several video segments like that, not for composites though, for the FEA, in the FEA playlist, and you can look at it. So user defined. So this corner, let me zoom in. This corner, I'm going to restrain 3 displacements. That corner, the other corner, let it move in the Y because it can shrink after the load is applied. That's okay. And the third corner, which is down here, or the other one, it really doesn't matter. This one does not move in the Z direction. This will take away the rigid body motion, and assuming that you haven't forgotten anything else, and I don't think you have, we're going to save this thing and we're going to run it. There. Remember I told you about those negative strength that Catia would not run? If you had put those as negative number for compression in the material properties, you get some weird message here, CPU cannot be estimated, blah, blah, blah. Anyway, it doesn't run. But we didn't do that. Okay, good. Finished. So look at the deformation. This is going to get stretched and shear. There we are. You can see that. Let's change the rendering here. Average ISO, material shading, view from the top. You can see, just like the previous problem, it's going to stretch and it's going to shear. Now, this number, the maximum deflection, should match the answer in video segment 2, the one that we did it with a single element. Fine. Now, Notice a couple of things here. First of all, let me deactivate that. Notice that we cannot plot. We cannot plot the stress, one meso stress. This is the one meso stress, because in composites things have to be done. It makes sense to do it layer by layer. Okay, so what I want to do is I want to plot the stresses, the components of stress in the different layers. So I put the cursor on the static solution case right there. See that? Right there. Right click, generate image. And then because I want to plot the stresses, let me filter it out. Stresses. So I'm going to plot the full stress component, nodal values. The other one is at the center, elements, centers, etc. Nodal values. Okay. Whoa. What the heck is that? All right. So let me double click on this. Double click on that. So what happened is that this is C11, that is for ply number one, lamina number one, C11, which is CXX. The only thing that is plotted in the local coordinate system, and I showed you, remember that thing that I showed you? I said, watch these arrows, 1 and 2 in the plane of the surface and 3rd in the normal direction, and the elements directions 1 and 2 kind of changed, etc. Because of that, that you get a weird thing like this. So we don't want to plot it in the local Cartesian coordinates. Let's, for example, do it in the global one. And that doesn't surprise you. The stress is 10,000 psi in the direction X. Direction X is the global direction X. It's not the fiber direction. It's not the transverse direction. If you look at C22, it's going to be 0. And if you look at C12, it's going to be 0. Let's put it back to C11. And if you go to other laminate number 2, it's going to be exactly the same story. Nothing changes because these two laminates are identical. They're identical as far as material goes and as far as direction goes. Okay, so let's put it back to lamina 1. Now, suppose we want to see the fiber stress direction, the stress in the direction of the fiber and transverse. Well, we cannot use global anymore. We have to go and select the local, the user coordinate system. Local one was no good. That's the one that we did before. And user, and for user, you have to go and select the coordinate system that you want. Remember, there was two of them. One of them was the Rosette. This is the one that I rotated by 30 degrees. So this is the one that's going to give me stresses in the direction X, which is along the fiber, 30-degree rotated. Okay, good. And we say, okay. Now, does that look familiar? 7,500, sigma 1, fiber direction. So if you go to C22, 2,500, does that look familiar? 2,500. The shear, C12, minus 4330, minus 4330, minus 4330. Okay, and it doesn't matter which lamina you look at because these are identical lamina. Just start with the top. Lamina 2, C11, 7,500. C12, 2,500. Lamina C12, which is a shear, minus 4330. These are identical to what we got with a single ply in the previous video segment. Now, we say, okay, no problem. Incidentally, this is why I prepared two video segments, not in this playlist, in the general FEA, which was called Tips About Plotting Stresses with Shell Elements. Okay, that's why these coordinate systems become important. All right, now, if you go here, once again, deactivate this, deactivate that, put the cursor there, right click, generate image, failure. I want failure criteria, and I'm going to do SciWoo 0.358. Does that look familiar? And this is exactly what I should have got with one ply in the second video if I had not made that foolish mistake. Let's do the other one. Another one for let's do generate image failure Hoffman 0.364. Well, 0.364, 0.365. Okay, let's round it off. And finally, another one. Put the cursor there. Oops, where is it? Right here. Failure. Maximum failure, maximum stress, right? Yeah. 0.357 and 0.357. Now, the reason this was okay with the wrong value that I inputted is that that does not depend on shear strength, but these two do. Okay. Yeah, I think that's pretty much all I wanted to do for this video segment. And good luck. There's not any free references like that on internet.